So my name is Mark Allen. I do work at AlertLogic. I do think that people are not using DTrace enough. There's probably a pretty good reason for that. Of all the people in the room, how many people deploy their Erlang applications on Linux? Okay, how many of you deploy things on not Linux? FreeBSD, Solaris. Of the people that picked not Linux, which is it FreeBSD or Linux or Solaris or something else? Anyone? Bueller? Ferris? What?
I don't think I go Solaris.
Yeah, Solaris. Okay, cool. So we'll talk about DTrace on Linux. The story for that with Erlang is sadly not good. But if you're using a Mac for your workstation, as I think most people are, or at least a majority of people are, not that there's anything wrong with a Linux workstation, then your options for using DTrace improve quite dramatically. So today I'm really going to try to introduce everyone to what DTrace is, to get familiar with what it can do, and really the goal for this talk is to introduce DTrace as a technology for understanding application behavior and for working on debugging your application. So it's not really so focused on wringing like every last juicy drop of performance from your hardware. There is going to be a talk later today by Rick Reed from WhatsApp, and he's going to give a taste of what DTrace can do to help you profile your hardware and help you tune Erlang and do all sorts of things like that if that's your interest. It's interesting to note that WhatsApp deploys their Erlang on FreeBSD, which is a supported DTrace operating system. But in any case, let's move on. And so the best place to start with is, what is DTrace? It stands for dynamic tracing. It's an observability technology. And what that really means is that it tries to give you a holistic view of your operating system. And that means from the top down and all the way back out again. How many of you have written code like this? Where you're writing a function, and maybe you take a fun or you take an MFA, and you basically try to time how long it takes for that function to complete or something like that. This is a really typical way for people to, kind of do some inline profiling or figure out like, okay, we have a bottleneck in this part of our code, and we really want to kind of try to get some more examination what it's doing or how it's behaving. So this is a really common approach, and DTrace lets you do this kind of profiling without actually instrumenting your code. So external to your Erlang program and built into the Erlang VM are a lot of DTrace probes that provide this kind of timing information. And we're going to get into that in some depth, hopefully as the talk proceeds. You guys all read this OTP Life, right? This is a Tumblr that's out there. It's really pretty funny. If you haven't checked it out, you should definitely go see it. It has this really hilarious slide, which I just lost, unfortunately. Yeah, I don't know what happened, but damn you, PowerPoint. Okay, that was awesome. Everyone liked that. Is this going to work? Play. Yes. So this is how dynamic trace can make you feel. I work at AlertLogic. We write a lot of Erlang code, and what I like to use DTrace for is exactly what I told you. We use it as a tool to profile behavior that's emergent from your system. So this is behavior that maybe you didn't anticipate, or maybe that you're surprised by, and you want to figure out exactly what's happening. You can get direct trace from your input all the way through the system and back out again. When I've given this talk in the past, a lot of people say, well, DTrace is really nice, but I like profiler technology X, right? I already have this way that I do it, and it's fine, and it's perfectly suitable for our needs. And my response to that is, yeah, that's great, and continue to use your profiler. What you should look at DTrace as another tool in your toolbox. So maybe it's not the end-all, be-all for your particular situation or your environment, but it is a great tool that can help expand your understanding of your application's behavior and how it actually interacts with other parts of your system. For example, if you have a database sitting outside of your application, it's really nice to be able to look at and see what kind of network connections that you're having from your application to that database in a way that you don't have to instrument inside of your application itself. So this is an external way for you to get visibility into things that are somewhat external to your actual application, like a data store, or like another downstream web service, or some other client that you're talking to out there, maybe not part of your direct Erlang application. Same thing with the debugger. A lot of people try to make this either or thing. I really look at it as a DTrace and other thing, whether it's a profiler or a debugger that you particularly like. Erlang comes with some really nice tools to help you profile process trees and let you look at supervision trees, even graphically, that are really neat. Don't give up using them, right? I'm not saying that this is a much better way to do it. What I'm telling you is that DTrace is a technology which you can add to your tool belt and then get interesting information out of your application. I talked about how this is an observability technology. Most of us have applications that sit up at the very top, and they talk to libraries, whether those things are written in Erlang or written in C. At some level, they hit the kernel, right, through system calls, and then they go into the kernel layer, and magic happens, and then all the things start from the bottom and go back to the top. And what you find out is it's turtles all the way down, which isn't a surprise to anyone in this room, I'm sure, but for a lot of people it is somewhat of a surprise, unfortunately. All right, so I told you there's some DTrace-enabled operating systems. Solaris 10, there's Illumos, which is a fork of Open Solaris, which sadly no longer exists. There's a couple of distributions of Illumos, which are slightly more popular. One is SmartOS from Joyent, another is OmniOS by OmniTI, and then there's FreeBSD and Mac OS X. And Mac OS X and FreeBSD have had DTrace probes for a pretty long time. Apple's had it since 10.5, and probably most of you are 10.8 or 10.9. So if you have a Mac right now or you're running FreeBSD right now, you can use DTrace right now. All right, so what if you're not?
So why do you just stick to DTrace? There is system tab on Linux.
Yeah, there are other observability technologies. What I have found is that, generally speaking, they're not as reliable and they're not as safe. And that's been a big problem in testing that I have done. I don't feel comfortable running a technology like SystemTap. And also, I don't develop on Linux. So as far as my personal workstation is concerned, I focus exclusively on DTrace. So that's why I'm focusing on DTrace only, not SystemTap. So SystemTap compiles its code into a kernel module, which is compiled by a C++ compiler, and then it's loaded into the kernel. And the quality of that is completely determined by automatic code generation. So it's quite possible that you can have SystemTap taps that crash your server, crash your development environment, do all sorts of bad things. I personally don't think that that's a risk that I want to take. Obviously, other people have other risk tolerances. That's fine. So, has that not been your experience?
No.
Okay. Well, good. That's nice to know. Yeah. So.
We developed a lot of infrastructure for DTrace support in OTP.
Yes.
And as part of that, we looked at SystemTap.
Yes.
We didn't experience any issues.
Okay. Well, good. So there's a report that SystemTap is as reliable and functional as DTrace, which is good to know.
The problem with SystemTap is that it requires very new Linux kernels, which most people don't have.
Okay.
Different problem.
Okay. So he's saying that the problem is that generally speaking, SystemTap requires newer kernels that people aren't running in production. Good to know. So maybe next year there can be a talk about SystemTap and Linux. So as far as Linux is concerned with DTrace, there are some DTrace technologies that are available in Linux. There's an open source loadable kernel module that you can do in development. And it's probably got about 60% coverage. It doesn't include support for application languages. And when I speak of application languages, I'm talking not just about Erlang, but other languages like Ruby, Java, JavaScript, Python, stuff like that's already also instrumented with DTrace probes. So for Linux, it's complicated, and I'm sorry for that. I hope that someday there will be a nice story for DTrace. There is a DTrace implementation supported by Oracle that's available in Oracle Linux. But quick show of hands, how many people in the room run Oracle Linux in production? Yeah, no one. So It's not at all clear that Oracle is going to contribute that to open source Linux, and even if they do that, it would be accepted. So it's not at all clear that the path for DTrace on Linux is clear, which is a real shame. So I wanted to cover some of the glossary terminology that DTrace provides. If you go and read the literature about DTrace, there's a lot of talk about a DTrace provider. And a provider is really just a word that means it manages probes. In the particular case of this talk, a provider is the application language itself. I think it's really important to understand that there are a lot of providers. If you go ahead and ask DTrace how many providers you have on a DTrace-enabled laptop, you can do that by using sudo dtrace -l, and then you pipe that to wc -l. Usually it's 50,000. On Solaris, it's up to like 100 to 110,000 DTrace probes that are available across a huge, actually mind-boggling number of areas of the operating system that you might be interested in. There's also probes. These are the observables that I keep talking about. We'll get more into what the structure of those look like in a second. And then there's the consumer. The consumer in this case is actually a D script. DTrace has its own scripting language, and it's somewhat awk-like. We're going to get into what it looks like in just a minute. In fact, right now. So the way that you do this is you essentially define a probe. There's an optional predicate, and there's also an optional action. And the actions are embraced clauses. DTrace supports a begin and end block, so that you can do things like initialize global variables. You can do aggregation functions. You can do sort and truncations at the end of your DTrace script. It also supports local variables. It has kind of a Baroque syntax for doing that. There's the this arrow foo equals some whatever value you want, integer, a float, a string. It also does aggregate and associative variables. Those are prefixed with an ampersand, an @ sign. I actually don't know what the typographic name for that is. And it also has one-liner support. You can do dtrace -n and then probe predicate action. So an example of what that looks like is this. It's pretty straightforward. In this particular case, we're using the Erlang providers. That's what the Erlang star means. The star means anything that starts with Erlang and then matches some arbitrary string. The colons that are in the middle here allow you to sort of zoom in on specific things that you care about. In this particular case, we're leaving them out because we want them to be wildcards. And the things that we're interested in instrumenting are process spawns, process exits, and exit signals. So these are all the things that we want DTrace to collect for us. This is really what it looks like inside of a program. Just to dig into this a little bit more, you can see that there's these copy and stir things at the end of the printfs. DTrace runs in an area of kernel memory, and the probes have these arguments that they provide. In the particular case of Erlang, the probes have not been well documented. So as an appendix to this talk in the slides, I have gone through all of the source code for Erlang and pulled out all of the DTrace probes and documented what their arguments are, what format they're in, like if they're strings or integers or whatever, so that people can consume them more easily. In this particular case, you can see that a PID is represented as a string, and that the MFA is also represented as a string, at least for DTrace purposes. So there's not like true Erlang terms here or whatever. And then same thing for the other things here. Copy and stir, I kind of got on a digression there. Copy and stir means take this argument value and stuff it into the special kernel memory space that DTrace has at its, to use, to consume. I'm going to go ahead and try my parallels live demo. As you know, things haven't worked out super well for that yet, but we'll try it one more time, and maybe we'll get lucky. All right, so okay, all right. I guess that's too big. There. This is really hard because it's not mirrored on my screen. All right, can everyone kind of see that from the back? Is that sufficiently large enough? Cool. All right, so I have a version of Erlang that I compiled. You can see over here that it says DTrace, just so you know that it's actually DTrace enabled. I can also do this, If I programmatically want to find out if DTrace is available, there's a module called DTrace, and if it is available, it returns true. If it's not available, it returns false. I'm sure that shocks everyone, but that's how it works. And then I'm already running a version of React back here in the background. Just to give you a quick flavor for what kind of things we've been doing, or at least what I did for the demo, is I have the spawn exit DTrace probe. And DTrace requires root privileges because you can actually spy on terminal sessions with it. You can actually connect to other people's process space and collect out their information from it, which means you can steal their cryptographic tokens and their passwords and their SSH keys and all sorts of other nasty things. So for that reason, when you invoke DTrace, it requires root. In this case, I'm going to invoke this through sudo. So you can see here that we have quite a lot of processes being spawned and being killed off. They're exiting for reason normal. If we were to quiet this down a little bit more, there's my pointer. I want to quiet this down a little bit more. I'm going to go ahead and kill that React process. Okay, and over on the DTrace side of things, we should see quiet. Okay, you guys saw there was like this giant flood of stuff that was going across the screen with all these PIDs being spawned and things being applied and stuff exiting because of normal. And now what I want to do is just show you real quick, like, you can see just starting the shell actually causes quite a bit of spawns. It shows you the whole startup sequence, what all the PIDs are doing, what they return as their exit value, what MFAs they're executing, what what messages are being sent from the sender back to the PIDs. So you can see that PID 28 sent a message to PID 6 that said, I exited because of reason normal. Here we have some reason no ents, right? Some file or something doesn't exist. We covered that in the keynote this morning. I didn't show it in this script, but you can actually use DTrace to find out why you're getting file system errors. And we'll cover like some of the interaction with other subsystems of the operating system a little bit later on in the talk when I do a more complicated perilous live demo. What I wanted to do here was just like do a spawn real quick. Like it is really hard to type when you can't really easily see what you're doing. Okay, so I'm just going to spawn a fun that sleeps for 2,000 milliseconds and then ends. And you can see that spawn into PID 33. And then if I go over here, you guys can see. Let me make sure that's scrolled down at the bottom. You can see down here we had PID 32 do some parsing, right? We did a spawn. And then inside the spawn, we had our remote call, timer, sleep. We had our argument, 2000. And then we got a message back to PID 25. And there's actually some kind of bug in the spawn exit collection tool. You can see over here, it kind of got chopped off a little bit. I don't know why that happens. It's probably a bug in the copying, the copy and stir argument, so that needs to be looked into at some point. But in any case, you can see the whole life cycle history of that function and how it lived and how it died and what messages it sent and whom it sent it to. And that's all good stuff. And I didn't have to instrument my spawn at all. I just kind of get it gratuitously for free, and that's really neat. You guys can probably imagine that there are a lot of cases where having that kind of observability would be really handy and useful, and that is in fact the case. So I'm going to go ahead and start React again, just so I don't forget to later on. what is it? Oh yeah, React. And then it's bin React start. All right, well, React won't be happy anyway because there's a cluster of 1. So it's a very sad camper right now. But that's fine. We'll just let it be sad for a while. We'll come back and look at this a little bit more closely in a little while. I'll see if I can leave this over on that screen and go back to the slides. See how well that works. There. Hey, cool. That worked fairly well. All right. How much time do I have left? 20 minutes? Less than that? Really? All right. I know I stand between you and lunch, so I hate that, but just bear with me. I'm going to skip over this. Those were in case my perilous live demo didn't work right. So DTrace also has a lot of common aggregation functions, super useful, that let you do all sorts of interesting aggregation and histogram type operations on them. There's average and count. Those do kind of what's advertised on the tin. There's lquantize, which is a linear histogram that it will generate. There's quantize, which is a log power of 2 histogram that you can generate. There's sum, min, max. There's actually about 10 other ones I didn't put on the slide. These are the most common ones that I see. As far as enabling DTrace in your own build of Erlang, probably the easiest way to do it is to use something like curl. You guys are all familiar with curl, right? Yes? No? If you're not, curl is a really nice tool for building Erlang releases. It's kind of modeled on Python brew or RVM or something like that. Virtual N for Python is another one that is a good analog to what curl provides to you. All you have to do basically is do the dynamic trace with DTrace. If you want system tap, which we talked about a little bit earlier, you can do dynamic trace system tap, and it will build the Erlang VM with those probes enabled. Once you get your thing built, you have to install it. So you just run the install command, and then you activate it. I also wrote a tool called Brew, and since I'm here, I'm going to toot my own horn a little bit because you're a captive audience, I guess. But I wrote Brew, which is a much simpler version of curl. It doesn't have all the bells and whistles. It also takes configure options and lets you install arbitrary versions of Erlang and use them, switch between them for a lot of convenience factor. So, for example, at my work, we're kind of stuck on R1404, which does not have DTrace support. And then if you want DTrace support in Erlang, you need to build with R15B01 or later, and you have to pass it that option. All right. So there's also a really interesting project called ErlTrace that I wanted to talk about for just a minute. This is running DTrace from inside of Erlang. So it allows you to actually create DTrace scripts inside of Erlang and then post-process the results inside of Erlang. It sounds crazy. It is a little crazy. But there is actually some good reasons why you might be interested in doing that. For example, you can push them into Folsom, which is useful. You can also send an alert if you want. You could have some sort of messaging mechanism to say that that thing's happening and that you care about, and you can kind of go and investigate it a little more closely. This is not necessarily a cheap thing. If you don't have headroom on your system to do this, obviously it's not a good idea. But it is an interesting project, and it's modeled on some capabilities that came out of Python and the Node environment. But it's nice to know that we have that same sort of capability in Erlang too. All right, I just wanted to spend a minute on interpreting output. You guys saw the screenshot from before that I glossed over. This is basically the same sort of demo here. I just wanted to talk in more detail about what's going on here in case it wasn't super obvious, because I know that there's a lot of stuff on this screen and it's not necessarily understandable what's going on. But you can see pretty clearly that you have PIDs getting created, that MFAs are being called, and that those PIDs are exiting in this next line down here with the full message that you can see. The sender is noted, the receiver is noted, and the reason is truncated because I mentioned it has a problem. But you can see all of these spawns occurring. You can see what their PIDs are. Again, they're treated as strings in DTrace, and then what messages go to which other actor, which other process. And that's really straightforward. If you look at this spawn exit script again, it kind of describes, okay, here's all the things I care about: spawning, exits, signals, senders and receivers, and what the arguments for all those things are. So just real quick, this is the things that are in the appendix. There's a process spawn probe, right? It has a PID and MFA. There's a process exit, PID, reason. You guys have already seen this. There's a sender PID, a receiver PID, and a reason. So all of these things are documented. Erlang has 41 probes, and I didn't want to talk about them all because that's all we would talk about if that's what we were going to do. So it's a little bit ridiculous. All right, so I've reached the point in the demo where I probably should ask for any questions before I go ahead and proceed with the Parallels Live demo. Yeah, go ahead.
Right now, all of the DTrace lines are all interleaved. Are there any good tools out there for correlating those and saying, I don't really care about them being time ordered. I kind of want to see them grouped by PID.
Sure.
Anything already out there like that?
Yeah, that's a great question. The question was, I don't really care about the time ordering of the DTrace output. Can you group them by PID? Unfortunately, the answer is not very easily. You generally are going to have to do some sort of post-processing. The way that DTrace is written is that it basically dumps everything to standard out, for better or worse. Now, you do have very much control over what format it actually comes out in. In the Parallels Live demo that I'm about to undertake, I've actually tab delimited all of the lines so that they're super easy to parse, in some other language, or you can do it in Erlang if you really want to. But doing the post-processing ETL operations in Python or Ruby or Perl or whatever your favorite thing is, probably not Bash, but one of those other languages is certainly appropriate to do. Yes, you can definitely say, I don't care about the time ordering. I want all of the PIDs to always be identified. And then you'd have to do that yourself as far as aggregating them and things like that. Is that not accurate? Okay. All right. Another question?
How much overhead does it add to run DTrace in build, and then how much overhead does it add to run DTrace?
Since I don't actually get to run DTrace in production, I can't really give you a good answer to that. What I can tell you is that on my laptop, running a DTrace-enabled Erlang as my day-to-day Erlang, I haven't noticed any problems with that at all. I'm sure that there's a potential for problems that were not envisioned. That's probably why it's not on by default. It's because the OTP team doesn't want to take responsibility for it. But as a daily driver, I haven't noticed any problems with it. As far as overhead in terms of running probes on stuff, if you have super busy systems, you probably don't want to let it run for a long time. But running it for 30 seconds or 10 seconds just to get a good sample is probably going to be fine. Again, your mileage may vary, but that's been my experience. Are there any other questions that I can answer before I try this again? Okay, all right, I'll give it another shot here. I think this is it. Yep. There's my mouse pointer. Okay, so I have React running over here. Hopefully, we'll make sure of that. I'll just do PS real quick. Or not, I guess. All right, we'll do this ulimit 496. That's better. Cool. All right, so that's running, and then over here, I want to show you the script I'm gonna do. I actually have two scripts, and I wanted to show you over here the I can't remember what I called this one now. Oh, I have act probe. Right, so I want to show you act probe. Okay, so there's a lot of stuff going on here in this slide, or this Vim DTrace script. Really what I'm doing here, just to break this down for you guys, is I want to replace all of these sort of standard Unix-y error messages with actual strings that make sense to humans. And then here's a note. You can see that this is all documented in the vnode. And then over here, the things that I care about. So we want an op create. So what this is going to do is go ahead and tell me anytime that the process that's named beam.smp is going to create or delete a file. And then it's going to go ahead and tell me the timestamp and the UID and the PID and the name of the process the operation, whether it's a create or remove, and then it will go ahead and give me the directory and the file name. So it'll tell me what files got written, where they got written to, whether it was created or whether it was deleted. And it will also give me a timestamp of that operation. Okay, so the next thing I want to do is actually look at some syscall accepts, and this is for networking operations. What I want to do here in this case is collect the information about syscalls into and out of sockets that are available through React. So anytime there's socket connections for React, I want to measure the latency of that socket connection. And that's what all of this code does. So we have accept entry and accept return. And when we do the return, that's actually when we compute the delta. You can see down here we're computing a delta. And that's in milliseconds, because DTrace comes with nanosecond resolution, or at least it's pretty close to nanosecond resolution. This is all basically low-level kernel-level stuff. Unfortunately, DTrace does require kind of that level of understanding the internal systems. I will tell you, as a person that doesn't have like super low-level kernel-level understanding, a lot of these scripts are available for Google searches. If you're interested in finding out about that, there's a really good collection of sites, and I'm going to talk about at the end of the talk, where a lot of this stuff can be found. So I'm only interested in internet IPv4 connections. I don't care about IPv6 connections. That's basically what that's doing. And then we're doing this NTOHS, which basically takes the binary representation of an IP address and turns it into a dotted quad. It gets the port number. There's the address, translation, same deal. And then down here, we're outputting our information. Again, we have a timestamp, PID, process name, the address family, the address, the port number, and so on, right? And then down here at the bottom, we're resetting our local variables. So that as things get reset, we reset our internal variables to 0, so we can calculate new latencies. So that's what that does. I'm combining both a virtual file system operation here and also a network level operation here. So that's one script. Okay, so I'm going to go ahead and run this. Act probe. All right, so that's running. And then over here, I have another script. I think it called it ETraceD. And this one does a lot of other interesting stuff. So in this case, what I'm interested in doing is calculating the latency of process scheduling. So as this internal Erlang scheduler throws new React processes, how long does it take for those processes to get scheduled? How long do they run for? And then calculate the delta. So tell me how long it took for a process, once it's scheduled, to execute all of its reductions, and then go ahead and tell me how long that took in microseconds. And then so we're calculating up here, we're grabbing the process start timestamp, and then process unscheduled when it gets thrown off the scheduler. We're calculating the elapsed time, and then down here we're printing that out. And we're also telling you that we unscheduled PID XYZ, whatever that is. I'm also interested in knowing when local functions get called. And what I'm doing here in this particular case is I'm aggregating them. So I'm doing a variable called lfunc, and I'm copying arg1, which is the MFA. And I'm just keeping a count of each one of those things, okay? And then same thing for global function entries. There's also one for BIFs, there's one for NIFs. So if you care about that stuff, you can get that. And then at the bottom, I have nblock, where I'm truncating the top 10. So it sorts it and then truncates them, prints them out, top 10 local and top 10 global. So that's what this script does. You guys can see that you can get as arbitrarily complex with this stuff as you want, with no additional instrumentation work on your part. All right, so you can see here that React is scheduling quite a lot of stuff. And what's really interesting to me is you'll see numbers over here that vary between something as low as like 30 and something as high as like 4,000, which is pretty cool to really get a sense for what that is. We're not printing out what the top 10 functions are, but when I hit Control-C to end this script, we're actually going to get that. as far as the other thing goes, there's a React admin function here that just runs some basic diagnostics. It runs a basic test, and it kind of tells you what stuff is broken and how you can fix things like that. It looks like I typed the wrong thing in, but that's fine. Let's see. Yeah, maybe I can just run diag or whatever. This is really hard to type this way. But. So we'll run another test, and we'll collect some more information about this. See if we got any output over here. Okay, so stuff's going on. You can see we're having quite a bit of connections. Like for example, we're writing a test called reagnostic in this directory called bitcask. There was a create and a delete. We also had 2 socket connections here through family 2, and they were successes, and it took 8 microseconds and 9 microseconds to connect. It tells you what their PIDs are. You got the timestamps over here, and these are all tab delimited, so it's pretty easy to post-process them and then correlate them together. Meanwhile, over here we have the Erlang side of things, which is very, very busy. And we're collecting and aggregating all this information. I'm going to go ahead and show you what it looks like now when I'm finished. And I hit Control-C, and what it actually does is it goes ahead and tells me the top 10 local functions. You can see there's some inline funds. They're kind of at the top. Those are the number ones. Number 1, 2, and 3, they're all React core functions. We have list, do, flatten. We have prop list, get value, which is interesting. List inth is another one that's high. File name, do, flatten. These are all areas where these are all sort of on the hot code path. That's what this is telling you basically. And then we have the global functions. So these are the ones that are external to the React application. They're part of the core library. Again, they're on the hot path. So if you were to look at this as an optimization opportunity, these would be places where you'd want to investigate how often, how frequently I'm calling these functions, and how long do they take to process the data. Okay, are there any questions so far? All right, so I'm going to go ahead and wrap up, I think. All right, here I am. All right. So Erlang DTrace Resources. There's the Erl install runtimes tools. DTrace comes packaged with a bunch of sample DTrace scripts that come with OTP release. They're gratuitous. They're part of the library. So that would be a good place to look. So wherever you put your installation, in the runtimes tools and the version string, there's a directory called examples. There's a bunch of DTrace scripts in there. The spawn exit DTrace thing that I showed you came out of that directory. And then a lot of the other things kind of mashed up together. There's also a README that's available if you're interested on the erlang.org website. And then there's a pretty good but somewhat brief talk that Andy Gross did a while ago for Basho Tech Talk about running DTrace on a Mac, specifically with Erlang, but just showed some of the specific Mac OS X visualization tools that come out of the box that are kind of neat. That's a really neat talk. It's pretty short. It's like 25 minutes, so if you really are interested in this, that would be a good thing to go see. As far as DTrace resources themselves, there's a really great lab that you can play around with from Oracle. They have this website called DTraceHOL.com. The HOL stands for Hands-On Lab. It has a VirtualBox instance that you can download, and then you can spin up a Solaris box, and there's like 13 exercises that you can run. It gives you a really nice overview and flexibility of all the different kinds of DTrace probes that are available in Solaris. Most of them are available in Apple products. Most of them are available in FreeBSD. Not all of them, but most of them are. There's a DTrace book that has a website called DTraceBook.com, surprisingly. There's also a language repository. Unfortunately, there's no Erlang chapter here, which is an oversight, but that's fine. As I said, the DTrace distribution in Erlang comes with quite a bit of sample scripts that are pretty good and tackle many of the same areas that you'd be interested in. The DTrace book, if you really want to get sort of the DTrace Bible, is at this link on Amazon. And then if you want to go to GitHub and see what they are, that's the URL for that. I wanted to throw out a plug again for Rick Reed's talk. He's talking at 2 o'clock this afternoon, and he's going to kind of give a taste of DTrace from the perspective of performance tuning. And that's, I think, going to be a really interesting talk. So if you're interested in learning how DTrace can help you tune your VM and tune your application, that would be great. And then that's what I have. So are there any other questions at this time? Yeah, in the back.
You said you had kind of somewhere documented all of the different DTrace posts that are available.
Yeah.
Do you have, was that just listed in slides? Is it available somewhere in your
Yeah, they're all right here. Yeah, there's 92 slides in this deck, and you guys have only seen 40 of them. So yeah, if you want to learn about all the probes, here they all are. We'll just go through them really fast. Yeah, so there you go. Are there any other questions? All right, thank you very much for listening about DTrace. Thank you, appreciate it.